Again, like I was saying about the notation, there's a bunch of different notation for how we might define or present the note, the derivative. All these different forms of notations are the same. Later, we're going to see a lot of this dy dx come in. We're going to see this y prime. And we're going to see this notation. I do not think we'll see this one, not in this class. That's more of an engineering type form. Matter of fact, that's the only time I've ever seen it. It's in an engineering book. So, as an example of using the derivative, let's say we want to find this derivative, or the derivative of 3x squared minus 2x. We start off by writing it out in limit notation, right? Using the limit definition. Say, all right, cool, we're going to pass x plus delta x through our function and subtract that from our function at x. After we expand everything out, we're going to drop out these parentheses. Then we're going to go ahead and find all of our cancellations. So for example, 3x squared, this 2x is going to cancel. And we're going to have the ability to rewrite this a little bit. And once all is said and done, that's where we're going to end up, right? We're going to say, all right, we've got a delta x in each of these terms. Let's factor that out. And that's going to cancel with our denominator. So we simplified it all the way down to here. But in the limit, as delta x goes to 0, we're going to end up with 6x minus 2. Now, what about this? Instead of x, here we've got t. What's this derivative? I claim that this derivative is equal to negative 2 over t squared. I claim this. Why don't you all spend about 3 minutes working on it, using the limit definition, see if you can find that answer for yourself.
Are you saying the negative 2 over t squared is the end result?
Yes.
Okay.
Whenever you see this primed, it means the derivative's been applied. What do you all think? How's it going so far? Okay, pro tip. One thing that'll help right away. Rewrite this as 2 times t to the negative first power. Rewriting these terms will oftentimes be one of the big keys to helping us solve these problems. Now, I'm going to go ahead and show the method for solving this. They don't rewrite it as t to the negative first. I think it's easier to work this out rewriting it, but looking at the solution. We start by saying, all right, we're going to take the function and pass t plus delta t through. That's where we get this first term in the numerator. Then we're going to take the function, subtract that from the function evaluated at t plus delta t. We're dividing all this by delta t. Excuse me. Well, if we look at our numerator, these things do not share the same denominator, right? So we have to rewrite the fractions in our numerator. The easiest way would be to multiply this term by t over t, right? And then this term by t plus delta t over t plus delta. Multiply by 1. So what am I saying? I'm saying to take 2 over t plus delta t minus 2 over t. I'm just working with the numerator here right now, okay? I'm not dealing with the entire fraction, just this numerator here. All right. Now this thing can be rewritten as 2 over t plus delta t times t over t minus 2 over t times t plus delta t over t plus delta t. But when we do that, what we end up getting is going to be 2t divided by t plus delta t, that quantity times t, right? Minus 2 t plus delta t divided by t times the quantity t plus delta t. Well, now we have shared denominators, so we can bring everything together in one fraction. So we have 2t minus 2 times the quantity t plus delta t over t times t plus delta t. Distributing this 2. We're going to have 2t minus 2t minus 2 delta t divided by t times the quantity t plus delta t. These 2's are going to cancel, and what we're left with is negative 2 delta t divided by t times t plus delta t. Well, we could rewrite this if we wanted to, but let's not do that just yet. So this is how they get to here. and then to here. Right? Notice then they get rid of this delta t. What they're left with is -2 t squared plus t delta t as the limit of delta t goes to 0. Setting delta t to 0, this thing turns into -2 over t squared. So, you might be wondering how I knew this was going to be our answer, because clearly I did not do that all in my head. That's not a thing. It's because there are rules that we're going to be using later down the road that will help make these problems easier. But for right now, I want to beat this into y'all. I want y'all to do this so much until your fingertips bleed, you hate me. But the reason why is because once that happens, when I show you the rules, you will be more receptive of them. You'll appreciate them more and more inclined to memorize, understand, appreciate, and remember them. Make sense? So, I'm gonna do this a bunch. A whole bunch. You're gonna hate me for it, but I have a reason for it. It's to make y'all more receptive on the other side. So, there's a point that needs to be made though. Not every function is differentiable. And by differentiable, that means it can be differentiated. You can apply the derivative everywhere. So there are a couple quick fail cases, things like when we have tangent lines that are vertical. Because what's the slope of a vertical line? Infinity, right? So if the slope of a vertical line is infinity, that tangent line can't possibly have a slope that can be found, right? Okay. Cusps. And if we think about this, it's going to be a little bit more obvious here. Coming from the left, our tangent line should look like it's going to be more and more negative, right? Negative, but increasing to infinity. Coming from the right, our slope should be positive, but increasing to infinity. So 1, coming from the right, is going to give us a positive slope approaching infinity. Coming from the left is going to give us a negative slope approaching negative infinity. So our limits don't agree here. Even though they both do give us straight lines, right? The straight lines have opposite derivatives. Does that make sense what I mean? Opposite in magnitude. One is positive, the other one's negative. So for that reason, the derivative fails to exist here. It also fails to exist here. Because here we have a line with constant negative slope. Let's say it's 1, because it's absolute value. And then coming out from the other side, we have a positive slope of 1. So coming from the left, our derivative would be -1. Coming from the right, it would be 1. The discontinuity at 0, which doesn't exist. In fact, the derivative of this looks like that. So just as a couple points, not everything is differentiable everywhere. There are some functions that aren't differentiable everywhere. There are some functions that are continuous and not differentiable anywhere, but are continuous everywhere. So this is to say that continuity does not imply differentiability, but differentiability implies continuity. So if you have a differentiable function, it has to be continuous. But a continuous function doesn't have to be differentiable. Does that make sense to everyone? This function, and this function are all three continuous. But they're not differentiable everywhere. So minimum condition for a function to be differentiable everywhere is that it is continuous everywhere. But it is not the case that it will always be differentiable everywhere, just because it's continuous everywhere. Cool. I know that was kind of word salad, but we're going to see more of what I mean as we go down the road. Differentiability implies continuity, but continuity does not imply differentiability. This is a very important detail, actually. Having said that, the end of the section. Now, we're going to get to the rules of differentiability. So how I was able to do this in my head. We get to all of these. These are great, but we're going to prove each one of them. Start off with the derivative of a constant is going to always be zero. Before I actually go through this proof, walk us through it, let's just think about what the graph of a constant function even looks like. Let's say we have f of x is equal to 1. Let's say that, right? What's the slope of that line? Just 0, right? Because this is actually in the form f of x is equal to mx plus b, where b is equal to 1 and m is equal to 0, right? So we already know the slope of this line is going to be 0. But to prove that the derivative is going to be 0, we're going to have to go about it this way. Setting our function equal to some arbitrary constant c. Let's apply the limit definition of the derivative. X plus delta x, our function is still going to be c, right? It's a constant. At x, our function is still going to be c. It's a constant. So this evaluates out to be c, and this evaluates out to be c. So we have c minus c. Delta x stays delta x. We have 0 in the numerator. So this entire fraction goes to 0. And it doesn't matter what delta x is, it's still the fraction 0. So it's always 0. So the derivative of a constant is 0. This is the constant rule. So if I ask you to find the derivative of the function f of x is equal to 4, well, it's a constant. The derivative is going to be 0. Right? Just as a couple quick examples, we've got 4 of them up here, written in all sorts of different notation, just to get us used to the different types of ways of denoting this stuff. Now, for this next definition, want to remember binomial expansion. This looks like a mess, I know. It's going to be really handy in just a minute. What we want to know, what we want to pay attention to is that we can factor out delta x from all these back terms, right? Factor out delta x here, we have x in there. So if we factor out a delta x from all of these back terms, we're going to still have a delta x here. We're going to have n minus 1 delta x's here, right? Make sense what I mean? So I'm going to erase all of this and write that down. X plus delta x to the nth power is equal to x to the n plus n times x to the n minus 1 delta x plus n times n minus 1 over 2 x to the n minus 1, or my mistake, x to the n minus 2 times delta x squared plus delta x to the nth power. Now, what to notice is that here we can factor out delta x to get n times n minus 1 over 2 x to the n minus 2 x to the n plus plus delta, delta x to the n minus 1. Right, notice I lowered everything by a factor. This is what we're going to use in just a minute, is that this can be rewritten as this. Okay. Now, what we're going to prove is called the power rule. Starting off, we're going to have f of x plus delta x minus f of x divided by delta x. Take the limit as delta x goes to 0. Oh boy, right away we run into that binomial form, right? X plus delta x to the nth power minus x to the n divided by delta x. Well, right away, we get a cancellation. X to the n, x to the n. We both cancel. So that means we're just left with these terms here. But each of those terms have a delta x. So when we factor them out, we get n times x to the n minus 1. This has been factored out. Plus everything like we wrote here. Agreed? This looks a lot worse than what it actually is. What we're doing is we're saying, and using this rule, we can factor out this delta x from these terms. We've got that delta x here. And what we're factoring out in the end is the shared delta x between these two sets of terms. So we can factor out this delta x and we can factor out this delta x. When we do, this is what we end up with. A, when we do that, that delta x is going to cancel with this delta x. So we're just left with this thing here. Just this. Because this delta x will cancel out with the delta x in our denominator. Everybody agree? So canceling these out, factoring out that delta x and canceling it with this, we get to here. But every term, except for your first term here, has a delta x in it. And we're saying delta x goes to 0. So this term goes to 0, the next term goes to 0, the next term, so forth, so on, until you get to the end. So the only term that doesn't go to 0 is this n times x to the n minus 1. Everybody please. So what that means then is that the derivative of x to the n is equal to n times x to the n minus 1. Let me start writing this down. The derivative of a constant is equal to 0. C is constant. The derivative of x to the nth power is equal to n times x to the n minus 1. This is known as the simple power rule. It's known as the power rule. They call it the simple power rule. I think the delineation they're making here is kind of an unnecessary one, but the book breaks it this way, so I'm not going to deviate from that, just so as to not confuse you all. All right, so we've got the simple power rule. Just as a couple examples of it, let's say we have the function f of x is equal to x cubed. And the derivative of this thing is going to be 3 times x squared. We're lowering that power by 1, and we're bringing that n down, right? Y is equal to 1 over x squared. Well, this is where that rule of rewriting things comes in that I was saying. Rewriting it like this, it's going to help us solve using power rule. Because now we can see, all right, our power is -2. We're going to bring -2 down. We're going to reduce our power by 1, so that's going to be to the -3rd power now, which is going to be equal to -2 over x cubed. when our function is just equal to t, x, s, whatever you want it to be. This is the first power, right? So pull that power down, reduce it by 1. This power then becomes 0, right? So it's 1 times t to the 0. So we get over here. Well, t to the 0 is just 1 times 1 is 1. We have r is equal to x to the 4th. Same trick. These really aren't agonizing once we see what the power rule tells us, right? But if we had to do this every time with a limit definition, screw y'all, I'm out, right? Like deuces, done. But the power rule makes this convenient for us. So if we now wanted to find the slopes for f of x equal to x squared at x is equal to -2, -1, 0, 1, and 2, just apply the power rule here and plug in x is equal to -2, x is equal to -1, x is equal to 0, 1, and 2. Does this make sense what I mean? So why is this? This is because the derivative is equal to the slope of the tangent line, right? And we can think of the tangent lines, the slope of the tangent line as being equivalent to the slope of our function at that value, right? Does that make sense what I mean? So the slope of the graph, technically it's not the derivative, but we can say it that way. We can say it that way because the slope of the tangent line is the derivative. The slope of the tangent line can be thought of as equivalent to how slanted your graph is, your function is, at those particular values. It's one of those hairy technicalities that I particularly think is an unnecessary note, but nonetheless, it should still be made. Distinction is really trivial, almost. I shouldn't say it's trivial. It is very minute. It's in the minutia that these technicalities really start showing themselves up. Start showing up. All right, so finding these slopes. We apply the power rule, and then evaluate at each of those x values. Power rule would tell us that the derivative of our function is 2x. So 2x, when x is -2, is going to give us -4. When x is -1, it's going to give us -2. X is 0, x is 2, x is 1, x is 2. All right, now, third rule. Well, this really isn't a derivative rule, this is a limit rule. We've already seen it before. The limit as x goes to a value of c times the function is equal to c times the limit of that function, right? We're going to use that here for the constant multiple rule. If we want to find the derivative of c times our function, well, applying the limit definition, we're going to have c times our function at x plus delta x minus c times our function at x. Well, notice up top you can pull out your c's. And because of the limit and how it behaves with a constant times a function, you can pull out that constant now. You just apply the limit directly onto your function. Well, hey, this is just the derivative of our function. So the derivative of c times a function is equal to c times the derivative of that function. That's convenient. I forgot to write c as a constant. Okay. So excuse me, let's apply this really quick. Let's apply this to A first. How would we solve A? To solve A, what we got is we're applying the derivative onto 2 times x to the 1/2 power well, rule 3 tells us we can pull out that 2. And rule 1 tells us that here we can bring down that 1/2, multiply it by x to the 1/2 minus 1 power, right? Everybody cool with this? Now, excuse me. That was a sneeze. In case that wasn't, I don't know why I felt the need to tell y'all that was a sneeze. Anyhow, 2 now times 1/2 x to the, this is going to become negative 1/2 power, right? The 2 is going to cancel with the 1/2. And we can rewrite this, if we wanted to, as 1 over x to the 1/2, or 1 over the square root of x.
Would either of those answers be correct, or just one?
All 3 of those.
All 3 of them?
How did you, so where did you do the, like, how did you get 1/2 minus 1 in the second section?
This comes from the power rule.
Oh, to the n minus 1, okay.
So let's compare. Check it out. The first thing they do is they pull out that 2, right? So far, so good. Then they apply the power rule. And then they go ahead and they rewrite it. First they simplify. And then they rewrite it. Like I said, all 3 of these are equivalent ways to write this. Is everybody cool with that? Dope.
So did that use the constant, multiple, and the power rule? So
We're going to constantly apply different rules. We're going to have in some cases where we're applying like 3 or 4 rules, some of the rules are gonna get applied twice or more. So just as a note here, let's look at B really quick. B gives us, we want to find the derivative of 5 over 2 to the x raised to the 3rd power, right? But before we do anything else, let's start rewriting things. Can we write this as the derivative of 5 over 2 to the 3rd, x to the 3rd, which is going to be the derivative of 5 over 8 times x to the 3rd which we can rewrite now as x of 5 over 8 times x to the negative 3rd power now we can pull out our constant, 5 over 8 d dx of x to the negative 3rd which is going to be 5 over 8 times negative 3 times x negative 4th power, which we can equivalently write as negative 15 over 8 times x to the negative 4th, or negative 15 divided by 8 times x to the 4th. Holy hell, there was a lot there, right? But what we're really doing is just rewriting things. Start off here, we say, all right, you can distribute this power to the 2 to the x. Well, 2 to the 3rd, that's 8. X to the 3rd, that's just x to the 3rd. Since x to the 3rd is in our denominator, we can rewrite it as x to the negative 3rd power, right? Okay. Well, if that's the case, 5 over 8, that's a constant that we can pull out. Let's pull out that constant. Apply now the power rule to x to the negative 3rd, it'll pull this power down and subtract 1 from it. So that's where we get this from. Now, negative 3 times 5, negative 15, negative 8, x to the negative 4. And rewrite it immediately. Nothing world shattering, right? So the general steps that they suggest, take your function, rewrite it. Then differentiate your function, then simplify the result of that derivative. Yeah.
Is that supposed to be a negative 4 at the end, or is it supposed to be positive?
Down below in the numerator, is that supposed to be negative 4 or positive 4?
This is supposed to be positive, right? Because x to the negative 4th is the same thing as 1 over x to the 4th. Make sense?
Yeah.
So
So,
we're really using a lot of algebra rules and some of our calculus rules, all thrown in together. But go
so
ahead.
why is it to the negative 4 and not to the negative 1?
Because applying now the power rule, d dx of x to the negative 3rd. This is going to give us
because it's just -3 minus
bring that
1.
down and then subtract 1, right?
Okay.
It's gonna give us -3x to the -3 minus 1. Which is equivalent to -3x to the -4. Make sense? So generally, the easiest way to go about these problems, rewrite your function. Start there. Start by writing your function, then rewrite it in the most simple way possible. The easiest way you can possibly think to identify what rules you might want to apply. Generally, that's going to mean writing everything in terms of powers. So fractions, rewrite in terms of negative powers, right? Radicals, rewrite in terms of fractional powers. Then differentiate. Go through and apply each of your rules as you can. Then simplify your result. So for example, let's say we wanted to solve B. We've got f of x is equal to 1 over 2 to the cubed root of x squared. All right. Let's start by rewriting the radical. It's going to be 1 over 2 x squared to the 1/3 power. Agreed? Well, this just this here, can rewrite this, can't we? Because we have a rule that x to the a, all that raised to the b, is going to be equal to x to the a times b, right? It's one of our algebra rules dealing with powers. So we're going to take advantage of that now. Let's say, all right, this thing is equal to 1 over 2 times x raised to the 2/3 power. 2 times 1/3 is just 2/3. Well, now, here, we can rewrite this as 1/2 times x to the negative 2/3 power. And now we can apply the derivative. Now, dx of 1 over 2 times the cubed root of x squared is equal to, we just rewrote it as dx of 1/2 x to the negative 2/3 power. Constant rule says we can pull out that 1/2. All right, so let's do that. Now, the power rule tells us that we can drop the power, right, down to a constant, make it -2/3 times x raised to that same power minus 1. This is going to come out to be negative. We're going to go ahead and deal with these constants really quick. 2/6 times x to the -5/3, right? And that's it. We can reduce it back into a lower form if we wanted to. That'll be suffice.
How did you get the last part?
So I dropped the parentheses and I multiplied 1/2
Oh,
by -2/3. That gives us the constant. And this comes from -2/3 minus 1 is equal to -2/3 minus 3/3 is equal to -2 minus 3/3 is equal to -5/3. Everybody cool? So let's check this, because I'm prone to mistakes. Once we differentiate, we get to here. Well, notice something happens. This isn't the simplest fraction, is it? We could rewrite this as 1/3 or -1/3. And that's what they did. They wrote it in terms of threes. But otherwise, everything else is the same, right? So really quickly, we have what's called the sum and difference rules. The sum and difference rule just says that if you have two functions, you add or subtract them, and you take that derivative, well, that's just the same as adding or subtracting the derivative of the two original functions. So let's say we have a function, call it h. H is going to be equal to f of x plus g of x. Then the derivative of h, well, that's h of x plus delta x minus h of x divided by delta x. Take the limit as x goes to 0. We can rewrite this as f of x plus delta x plus g of x plus delta x minus f of x minus g of x divided by delta x. Well, we can rearrange the terms up here. We can group the f's together and we can group the g's together. That's what they've done here. Then we can break up these two fractions. But if we break up these two fractions, then we can break up the limit as well, right? We can apply the limit to each of these terms independently. Well, that's just like finding the derivative of f and the derivative of g and adding them back together. So the fourth rule says d dx of f of x plus or minus g of x is equal to d dx of f of x plus or minus d dx of g of x. That's convenient. Because now, let's think back to an earlier problem we had. F of x is equal to x squared plus 1. Now, if we want to find the derivative of this thing, well, that's going to be equal to the derivative of x squared plus the derivative of 1. Well, this, by rule number 1, is equal to 0. And this, by rule 2, is just going to be equal to 2x. So the derivative of our function is just going to be 2x. Now notice something here. This is exactly the same derivative as the derivative of x squared. I point this out because let's say down the road, because we will, we want to go back from the derivative to the original function. Notice we can't necessarily do that because more than one function has this as a derivative. So which one of those one function gave us this derivative? Was it x squared plus 1? Was it x squared? Was it x squared plus 3? Was it x squared minus pi? Was it x squared plus whatever you want as a constant? You don't know. So we can't necessarily go back from the derivative to the original function. We can go up to the original function plus or minus a constant. So just keep this in mind as we look forward. Because we're going to want to eventually undo derivatives. Now, having said that, I think this is a natural break point. So let's take a quick break, make it about 5 minutes, catch your breath, relax a little bit, stretch your legs. And we'll come back to the last 30 minutes of class.